Our topic is talking about the electric flux and its applications. The word electric flux is a measure of flow of electric field through a given area. And this electric flux is proportional to the number of electric fields going through a normally perpendicular surface. If we consider a charge, a positively charged, now take note that positively charged radiate outward to the space. So the question is, do we have the electric flux? The answer is no. Why? Because flux depends on the area. It is the measure of electric field through a given area. So since there is no area, then there is no flux. And remember that this flux is proportional to the number of fields. So the greater the number, more fields, more flux. So therefore, in order to produce flux, we need the area. So suppose again we have this charge, and we will enclose that charge to a box. So the question is, do we have the flux? The answer is yes, because there are fields that can be measured through an area of a cube. We have 6 sides of the cubes, and each sides have electric field on it. So if we quantify this electric field on that area, we are measuring the electric flux. Flux is a scalar quantity, which means that it has magnitude, but there is no direction. If we calculate the flux, we have negative values, we have 0, and we have positive. So the question is, what makes the flux positive, and what makes flux negative, and what makes them 0? So those are questions that we need to answer. Now in this module, we need to derive the formula for the flux, for a flat surface, and for a uniform electric flux. Then after that, we will proceed to the non-uniform electric flux. And after providing the concept on this electric flux, we will solve problems. We will solve and apply the principle of electric flux. Now, look at again what's the difference of having two charges inside the box compared for the one charge only. So the answer is, if we have more charge, we have more electric fields. So if we have more electric fields, we have more electric flux. Because electric flux is proportional to the field, and the field is proportional to the charge. It is also proportional to the area. Why? If we have a wide area, then we have more fields to be counted. So therefore, more area, more flux. Now, let's consider the flux of an open surface with a uniform electric field. So suppose we have the uniform electric field going to the right. And suppose we have this area. So the question is, once electric field intersect to the area, the question is, do we have the flux? The answer is yes. Why? Because we have this flux and we have the area. So quantifying the amount of the flux, it is actually talking about the normal area. Normal area means it is the vector perpendicular to the surface area. So if we quantify the amount of the flux, we are concerned with that normal area as the vector and the electric field. The magnitude of the normal area is the area of the plane. So the amount of flux depends on the electric field vector and the normal vector. So in this case, our angle from the electric field going to the normal area is 0 because they have the same direction. So a line that have the same direction, the angle must be 0. So if we quantify the amount of flux, this is simply as, by definition, the electric flux of a uniform electric field or non-uniform electric field, generally called as the dot product of the electric field and the area vector. Take note, area vector. This is normal to the surface area. So, quantifying the amount of how much electric flux present on that electric field on the area, the answer is, it is electric field dot product of A. E dot E dot A. So, the principle of that product is actually multiplying the magnitude times the cosine of the angle between them. So, therefore, in terms of its magnitude, the flux can be calculated by the product of the magnitude of the electric field multiplied by the magnitude of the area, normal area vector, which is the area of the surface area, and multiplying by the cosine of the angle P. Take note, the angle P is the angle between it is coming from the electric field going to the area. So in this case, our P is 0, so therefore the cosine of 0 is E. Which means that in this orientation of the plane, we are providing the maximum flux. Maximum flux. Why? Because the cosine of 0 is 1, and the greatest number that can produce for a cosine or a sine is only positive 1, or maybe in the lowest of the negative 1. So what will happen if we change the orientation of the area? Suppose, because the plane area is perpendicular to the electric field, so therefore the normal area is parallel. That's why it produced 0. So the question is, what will happen to the electric flux if we change the orientation of the plane? So most probably, the flux will change. The question is how much? Now in this case, if we incline the angle of the plane at an angle of P, so therefore there was an angle between the electric field and the area vector. So therefore, if we have the electric field strikes to the area, then again we have the electric flux. Quantifying the amount of electric field within the area is the flux, remember. But if we compare this before, the collected fields are more than the collected fields with an angle of P, which means that the electric flux now is less than compared as before. So look at the formula. We can still use this formula. The electric flux is equal to the electric field magnitude multiplied by A, which is the area of the surface. Then multiplying the cosine of the angle. So if this angle is not 0, then this cosine is less than 1. So therefore, it will produce less magnitude or amount of flux as compared before. Okay, so let's continue changing the position of the area surface area. Suppose the plane now becomes horizontal. The question is, do we have the electric flux? So when we orient the plane into horizontal, so this means that the normal now is perpendicular to the field. So if it is normal to the field, it is normal to the area, so meaning it is now perpendicular to the electric field. So therefore, the angle must be 90 degrees. So the question is, do we have the flux? The answer is no. The answer is 0. Why? Because the cosine of 90 is 0. So if you multiply everything here, the flux becomes 0. So therefore, if the normal vector is perpendicular to the field, the flux is 0. So it is talking about the angle of the normal, the most important. Take note, if the angle is 0, it provides a maximum flux. As the angle increases up to 90 degrees, then it will keep on reducing until 0. Now suppose What will happen if the area is beyond the 90 degrees? What will happen to the flux? The flux now becomes negative. Okay? Because for a cosine function of an obtuse angle, the value is negative. So therefore, when we say a negative flux, it is the normal is opposite direction with the electric field now. So therefore, if you want to produce a positive flux, it should be from 0 to 90. If you have the angle 90 to 180, then the flux is negative. So as I've said before, there are three possibilities of having electric flux. It can be positive when? If the angle is between 0 to 90. Now, if your angle is between 90 to 180, the flux now becomes negative. And your flux becomes zero if the angle is exactly 90 degrees or 270. Take note, 270. Because 90 and 270 are angles that are perpendicular to the initial point. Okay, so therefore, the general formula for the electric flux from a uniform electric field is QE, or the electric flux is equal to E times A cosine P, where E is the electric field uniform, A is the area, okay, and the angle P is the angle from the electric field going to the normal of that area. Normal to that area. Okay, so what will happen if your electric field is non-uniform? If non-uniform, then we need to, you can still use the formula before. Remember E electric field dot A. So since the electric field is not uniform, then we will consider only the infinitesimal area vector. We have to consider a very, very small area so that we have a very, very small normal. Then we will take the dot product of that E electric field, which is non-uniform, that electric that normal infinitesimal area. Then take the integral of that. Then we have the total electric flux. Take note that if we take that product of the infinitesimal to another value, the result will becomes infinitesimal. So therefore, this must be an infinitesimal electric flux. So we want to extend this to the total flux. So we have to integrate both sides, and this will be the results. Okay, so take note that these are in terms of vectors because this is a dot product. By the principle of dot product again, we can change this to E because E, therefore, if we take the dot product, it should be the perpendicular. It should be the parallel. It should be the parallel uh, vector to what? To electric field should be parallel to differential area. So therefore, we use the E cosine P, where P again is the angle from electric field going to the area normal. So therefore, the electric flux is the integral of E cosine P infinitesimal A. This is the formula of finding electric flux of an open surface with non-uniform electric field. Okay, so in order to verify how far we are from the concept of the electric flux, let us consider this problem application. Consider a desk of a radius of 0.10. So this is the desk is oriented, take note the radius is 0.1. Oriented with its normal vector in. We use in vector. And this is oriented at a 30 degrees. Take note this is 30 degrees from the uniform electric field. The electric field is uniform and given as 2 times 10 raised to, or 10 raised to 3 Newton per coulomb. Okay? Then, you are asked to calculate how much is the electric flux through the in the presence of the electric field, uniform electric field. So, given the electric field, given the radius, given the angle P. This is the 30 degrees is the P. So therefore, and this is uniform. So recall the formula. The formula for the electric flux is EA cosine P. Substituting the values for the electric field, which is 2 times 10 positive 3 Newton per coulomb, and we have the area. The area is circle. So the formula for the area is pi r squared. So take the pi, multiply it by the square of the radius. The result is A. Then cosine of P. P is the angle between A and A. So this happens to be 30 degrees. So therefore, substituting all those values, then we can, by the way, the area is 0.0314 after multiplying pi with the square of r. So simplifying further, we have 54 Newton meter square. Take note, this is the unit of flux. Why? Because the formula is the product of the electric field and the area. So electric field has a unit of Newton per coulomb. Sorry, this is Newton per coulomb, Newton meter square per coulomb, because electric field, kindly correct this one. This is 54 Newton per coulomb meter square. Okay. Now in letter B, you are asked to calculate the flux, but this time you are asked to turn the normal in such that the orientation becomes now perpendicular to A. So when we say perpendicular to A, the angle must be 90. So therefore, this is now the orientation of the plane. It is, the normal is perpendicular to the electric field. So therefore, the area must be parallel to the field. So the angle must be 90 because the angle is coming from electric field going to the normal always. So using the formula, we understand that the cosine of 90 is 0. So substitute the values, then the result is 0. In the final question, you are asked to find how much is the flux if we turn again. But this time, the normal should be in a parallel to E. So therefore, the angle is 0. So if the angle is 0, use again the formula to solve for C. We have this maximum value of 63 Newton meter square per coulomb. So take note, 63 Newton meter square per coulomb, the unit of the electric flux. Okay, so the question is, what is now the electric flux if the surface is not flat? Suppose the curve, the surface is a curve. What will you do? So in this example, we are about to find the uh, a point charge surrounded by imaginary sphere of radius r centered on the charge. So we are asked to find the resulting electric flux through the sphere. So meaning, if we have a charge, for example, then this is given as Q, and this charge was enclosed by an imaginary sphere whose radius is r, and the charge was placed at the center of the sphere. Question: calculate the electric flux due to this charge at the surface of the imaginary sphere. Okay, so how will we solve this one? Now take note, this is a curved surface. So if it is a curved surface, we have to consider an infinitesimal area. So therefore, we will use a very, very small area. So therefore, calculating the flux, take note, it requires the electric field at the surface and the area. And the area should be an infinitesimal area. Now take note that electric field is already calculated before this topic. So electric field, if you ask what is the electric field at the distance r, Take note, you have to recall your previous physics. The electric field, the electric field of a point particle whose, with radius r is 1 over 4 pi permittivity multiplied by discharge divided by the square of r. Let's go back to your old books. So therefore, we have to consider an infinitesimal area at that point. So therefore, with that, we can say that this is no longer a curve. This is a flat surface because this is a very, very small area. So therefore, normal to that is the vector, area vector, the differential infinitesimal area vector. So we can use the formula before. So we have to take the dot product of the vector E dot the infinitesimal area vector. So this is now the definition of the flux. But if we multiply these two, very, very small, then we will producing a very, very small electric flux. So in mathematics, we can expand the value of E by integration. So integrating both sides, substituting, using the magnitude of E and magnitude of A area, vector area. So we come up with E cosine of P. Again, this angle is the angle between the electric field and the area, normal. So integrating both sides, the limits of the flux ranging from 0 going to the extended value of the flux, then integrate both sides. So therefore, take note, this field is constant at that point, the same point of the radius r. Cosine P, and this is the infinitesimal A. Now again, as I've said, electric field is by definition is the 1 over 4 pi permittivity Q over R squared. This is the electric field of a point charge. So this must be substituted here, and the angle P is 0 because the two vectors are parallel. So substitute everything. Okay, this will becomes 1 over 4 pi r Q over R squared cosine of 0 dE. The integral from 0 to 4 pi r squared. Why 4 pi r squared? Take note that the infinitesimal is area. Okay? And this area, if we extend this area by integration, it covers the whole surface area of a sphere. So the question is, what is the area of the surface, spherical surface? Surface area is 4 pi r squared. So therefore, we will run this calculation ranging the area starting from 0, then expand it until such that the area becomes 4 pi r squared. So with that, we are calculating the electric flux in the entire area of the surface. So do the evaluation of the integral. So therefore, we have changed these are constant, so we can take it out, and the only integral inside is only the 1 unit of infinitesimal area. So evaluate integral. So therefore, we come up with 1 over 4 pi permittivity Q over R squared. And take note, evaluate the limit from upper minus lower. So this is 0. So therefore, this is simply 4 pi R squared. Now notice that we can cancel the 4 pi also with the R squared. So what is remaining? The flux now becomes Q over permittivity. Now take note, Q naught is the permittivity of a vacuum, and it has a value. Take note, the value is 8.8 times 10, 8.854 times 10 raised to negative 12. The unit is coulomb square per meter per Newton meter square. Again, if you are asked to calculate the how much is the flux, it is simply as the charge over the permittivity, where the permittivity is again 8.854 times 10 raised to negative 12. The unit is coulomb square per Newton meter square. Okay, so these are the application problems for calculating the flux of a plane surface and a curved surface. To sum up with the discussion is, Take note nga the flux requires area. There is no flux if they have no area. Then, in a flat surface, we can calculate the electric flux through the formula of the electric field multiplied by that area times the cosine of the angle between the two vectors. The normal vector is the normal area. Normal to the surface area is a vector. So, the angle between them is P. Now, if we are calculating the electric flux for a curved surface, then we need to consider the infinitesimal value. So, we will be going to use the principle of calculus, the integral calculus, in order to evaluate the differential equation because we are using infinitesimal value. It is a kind of a differential equation. Solution of a differential equation requires integration. So, therefore, these are the applications to the principle of the electric flux. Now, in order to review or in order to verify how far are you away from this concept, then you are encouraged to solve this problem. These two problems are problems on a flat surface, and another problem is a problem on an spherical surface. Okay, good luck for your for answering this problem. See you next time. Thank you.